Welcome to lesson 2.8b. Today we're going to look at naming type 2 binary ionic compounds, and type 2 binary ionic compounds will contain metals or metal ions that can form multiple cations. So the charge of the metal cation is indicated by Roman numeral in the name. Notice it says down there at the bottom of this slide that common metals that don't require Roman numerals, your group 1s don't require Roman numerals because they're always a +1. There is no ambiguity there. Group 2 forms +2. Aluminum only forms a +3, and you can add gallium to that as well because gallium only forms a +3, and then silver and zinc only form a +1, +2. You'll see at the end of this PowerPoint a table that gives you some common ions of different metals. It used to be when they would name these ions, instead of using the Roman numeral system or what they call the stock system, they would say the ion with the highest charge ended in "ic" and the one with the lowest charge ended in "s." So that's where we got things like stannic chloride and stannous chloride, and that would indicate tin, or ferric chloride and ferrous chloride. So a lot of they could. So basically it changed the name of the cation and it changed the ending, and that was confusing, so we went ahead and went to the stock system. So let's look at a few examples here. We're going to try to name some, and then we're going to take the names and we're going to write formulas for those names. So if you want to pause and try these on your own, you're more than welcome to, but there are some other examples towards the end of this PowerPoint where you can do that as well. All of these compounds contain a metal that can form more than one cation, and in order to figure out what the formula, what the name would be, you have to know that compounds are electrically neutral, which means the positive parts must exactly balance out the negative parts. So in copper, in this formula right here, chlorine is in that column on the periodic table where they're always a -1. So if you have a -1 on this half of your compound, then this half of your compound has to be a +1. So that's why we name this copper 1 chloride. Same kind of reasoning here. In mercury, this mercuric oxide, notice there is an oxygen here. Oxygen's in the column that's always -2. So to balance out this -2, this half of the equation has to be a +2. And so this is mercury 2 oxide. This last one, a couple different ways we can do this one. Notice it does have two subscripts. One way is to do mathematically and look at balancing. So as we said before, oxygen is a -2. So the total minus on this compound is -6 because I have 3 -2s. So that means the total positive part must be a +6, and since I have 2 irons, each of those contributes 3 to that +6, and so this is iron 3 oxide. Another way I encourage my students to do this is something called the crisscross method, only this is kind of like the uncrisscross method. So if I have iron in my compound and I have oxygen in my compound and I have these numbers down below, if I can move this up here and this here, then that tells me that the iron is a +3 and the oxygen is a -2. This almost always works. There are occasions where it doesn't work, and you're going to see an example on the very next one where it does not work. Manganese 4 oxide. So how do we write this compound? We'll use that crisscross method again. So manganese, what's the charge on that manganese? It's a +4. What's the charge on an oxygen? It's a -2. Well, if I crisscross those, I end up with Mn2O4. But that is not the smallest whole number ratio, so I can reduce that to MnO2. And when you're dealing with ionic compounds, especially binary ionic compounds, your subscripts must be in the smallest whole number ratio. In covalent compounds and in organic chemistry, you'll see that you could have 2s and 4s and 6s and so on, and that's the way the compound should look. But in binary ionic compounds, these have to be the lowest whole number ratios. And just remember, this doesn't happen very often. That crisscross method works most of the time. So on lead 2 chloride, the symbol for lead is Pb. We know it's a +2 because it tells us in the name right there. And then chlorine is Cl, and it has a -1 charge. So if you cross those, and we're leaving the charges off when we cross them, we're not going to put a 1 down there because a 1 is implied. But on the chlorine, we're going to put a 2 there because we crossed that down and we put a 2. So you'll find if you go back and do that mathematically, you'll see that's also charge balanced. This is just a critical thinking question in terms of, so those transition metals on the periodic table, that's where most of your having more than one possible charge is. And how would naming compounds be different? Pretty easy question to answer because we wouldn't use the stock system. There'd only be type 1 ionic or type 1 compounds. The textbook that I'm pulling these PowerPoints from, pulling the material from, is pretty good about providing flowcharts. So when you look at this flowchart, is it type 1 or type 2? Type 1 is the type of element or cation that only has one charge, one possible charge, so you just use the cation using the element name. Type 2, you figure out the cation charge and then you put that in Roman numeral. So as I promised, here's a couple more examples. So again, you can stop on this one and then we can talk about that, or we can you can just go on to the next slide and listen as I talk through that. Now please note that in terms of naming compounds, you've got to practice them. And you'll notice on this particular slide that cobalt is a transition metal, so it's found in the middle of the periodic table. Calcium is in group 2. So it's mixing type 1s and type 2s, and you have to figure that out. So let's look at the next slide. As I mentioned earlier, cobalt is a transition metal. You don't know what charge it is until you figure out that bromine's a -1, total of -2 here, so that has to be a +2. On this one, we know calcium is in group 2, or the alkaline earth metals, so it's a +2, and we don't need any Roman numerals, so this is just simply calcium chloride. When we work the other way, when we work from chromium 3 chloride, remember we can use the crisscross method. So Cr is a symbol for chromium. It's a +3 because that Roman numeral tells us that. Chlorine is a -1. So if we cross those, we end up with C excuse me. We end up with CrCl3. And then gallium iodide, same kind of thing. I said earlier, gallium is always a +3. It's in that same row as aluminum. Iodide is always a -1. So if I cross those, I end up with gallium, or Gai3. And this is the chart I promised, or I told you would be at the end of the PowerPoint. Notice the charges on the elements. As we get over here, the -1s, the -2s, the -3s, the blue are your type 2 cations. They can vary. On that one of those first slides, it included aluminum, but it didn't include gallium, but those are always +3s. It included silver and zinc, but it didn't include calcium, so just remember those are always +1 here, or +2 here, +3 here. And one of the things that I encourage students to do is I encourage them to go to their periodic table and write a +1 here, a +2 there, a -1 here, -2 there, -3 there. And then in these boxes, I encourage them to go ahead and write the charges of these metals that are always the same charge. All right, well that completes lesson 2.8b. On 2.8c, we're going to move on to polyatomic ions.